Okay, so this is our first video on the simplex algorithm. The first thing we need to address here is the standard form of a linear programming problem. Okay, so usually we write these as maximum or minimum of some equation, some linear equation. So that's going to be our objective function. So z is going to be some sum from j equals 1 to n of some coefficient j times some variable, right? And this is going to be subject to a whole bunch of stuff, right? So this is going to be also subject to a bunch of linear inequalities, right? So they're all going to be of the same size, j equals 1 to n, right? And we're going to get coefficient aij, so we're going to get a system of linear inequalities here. Xj less than or equal to bi, where I is going from 1 to m, right? So we have m constraints, all less than some n constants, right? So, or m constants. So we're going to also make it so that all the xj's are positive, all the bi's are also positive, and that's kind of how we work with this. Now, unfortunately, this is not ideal for matrices because of those inequalities. So what we do is we rewrite these. The objective function does not change. It's fine. It's an equation. So that's still going to be j equals 1 to n cjxj. But now our constraints are going to get written as a system of equations. And we do this by introducing some what we're going to call slack variables. So this part stays the same, but for each equation we're going to add a slack variable, so an SI, okay? So, and that's going to allow us to turn this from an less than to an equal sign. So there has to be some value that's going to make these two things equal, some positive value that makes that work. And then we get bi from I equals 1 to m, and now we're going to require all the xj's to be greater than or equal to 0, all the bi's to be greater than or equal to 0. And like we said, if we're adding these in and we're going from less than to equal to, then these have to be positive. So all the si's have to be greater than or equal to 0. So this is our new vision for how a linear programming problem works. So we go from inequalities to equations in the constraints by adding these arbitrary slack variables. So let's give a specific example of this. We have, we're going to maximize z is 4x1 plus 6x2 subject to negative x1 plus x2 is less than or equal to 11. x1 plus x2 is less than or equal to 27. 2x1 plus 5x2 is less than or equal to 90. And x1 and x2 are positive. Okay, so we rewrite this as maximize z equals 4x1 plus 6x2. And then we start throwing in these slack variables. So this is going to be subject to negative x1 plus x2 plus some s1 is going to be equal to 11. x1 plus x2 plus some s2 is equal to 27. 2x1 plus 5x2 plus s3 is equal to 90. And now x1, x2, s1, s2, and s3 are all greater than or equal to 0. So this is how we write this. Now, the total advantage of this is that I can rewrite all of this as kind of a sophisticated augmented matrix. So let's take a look at what that looks like. Okay, so to build my augmented matrix, I'm going to put the constraints in the top. So the first constraint was negative x1 plus x2 plus s1, and that had to be equal to 11. Okay, and now I get x1 plus x2 plus s2 was equal to 27, and then 2x1 plus 5x2 plus s3 was equal to 90. So there's my constraints. And then down here at the bottom, I'm going to put in my objective function. Negative 4 minus 6, negative 4x1. Okay, so what's happening here is these have to be negated. Because my objective function was originally 4x1 plus 6x2 was what I was trying to maximize. But in order for this to work with our algorithm here, we have to negate the objective function. So wherever I had a 4x1 and a 6x2, we're going to put a negative 4 and a negative 6. There are no slack variables in the objective function. And when we start here, we're actually starting with a 0 value down there. Okay, so I'm going to add some labels to this. This is now going to be the x1 column, the x2 column, this is the s1 column, the s2 column, the s3 column, and going across, so we'll just call this B for right now. Going across, this is the row that has the first slack variable, the row that has the second slack variable, the row that has the third slack variable. This location right here is Z. So this is how I read this table. Currently, neither x1 or x2 have a value. Okay, so x1 and x2 are both 0. Well, if x1 and x2 are 0, then s1 has to be this. It has to be 11, because 0 plus 11 is 11. Okay, s2 has to be 27. S3 has to be 90, and the Z value is 0. Okay, so if you think about this in terms of our graph, this is kind of what's going on here, is you have this graph of the feasible region, which is that polygon, right? And we're at one of the vertices of the polygon. 0, 0 is actually feasible in this problem. So we're at that vertex. So that's our location, 0, 0. Our objective function at that location is 0. So it is at a vertex, right? But we're definitely not optimal, okay? And here's how we're going to know if we are optimal or not. If there is a negative in the bottom row, so there's a negative value left in the bottom row, we are not at an optimal position here. So since I have a negative 4 and a negative 6 down there, I know that I am not optimal. I have a way to go upward. So now what we need to do is we need to have an algorithm that's going to move me from 0, 0 to some other vertex that's on that polygon, and I want to do it in such a way that each time I move from one vertex to another, the Z value goes up. And this is exactly what the simplex method does. So what you have to do is you have to figure out what are the entering and exiting variables of a pivot. Okay? So finding the entering variable is not hard. Okay? The entering variable is the column with the most negative value at the bottom. So this is going to be the x2 column here. It has negative 6 at the bottom. So this is x2 is my entering variable. So one of these slack variables is going to go away, and x2 is going to take its place. Now the question is which slack variable? Okay, so what you do is you want to find the row that has the smallest non-negative bi over aij. Okay, so this row, the bi over aij, is 11 over 1. Okay, that's just 11. The S2 row has 27 over 1. So that's just 27, right? And the last one here is 90 over 5, right? Which is, I think, 18. So the one that has the smallest non-negative one is that 11 there. So this is my exiting variable. So we're pivoting on this value right here. And the x2 is going to end up over here. The s1 is going to end up over here. Okay, so what does that mean to pivot? Okay, so in order to do this, I'm going to get rid of some of this stuff down here at the bottom. Okay, and I'm actually going to pivot the matrix by hand. Okay, so if I do this, what I want is I want that pivot to be a 1. Okay, so that's helpful. Okay, so I have a negative 1 here, a 1 there, 1, 0, 0, and then I drop down an 11. So that's already a 1. So that's great. Okay, now I want to do this so that everything else in that column is a 0, which means this is like row operations again, right? So I want to subtract the top row from the second one. So 1 minus negative 1 is 2. 1 minus 1 is 0. 0 minus 1 is negative 1. 1 minus 0 is 1. 0 minus 0 is 1. 27 minus 11 is 6. Okay, so I want a 0 here. So I'm going to multiply the top row by negative 5. And I am going to add that to the third row. So let's see, negative 5 times 1 is 5 plus 2 makes this a 7. It's going to make that a 0. This is a negative 5, a 0, a 1. Let's see, it's going to be negative 55 plus 90 gives me 35. And then I'm going to do this again with the objective function. So I need 6 plus 6 is 0, right? So negative 6 plus negative 4 makes this negative 10. All right, let's see. That's going to be 6, 0, 0, and 6 times 11 is 66. Okay. So the exiting variable was the x sub 2. So this is going to pivot with s sub 1. And x sub 2 goes over here. And everything else stays, where it was. Okay. So, the top, these don't exchange actually. This still remains x1, this still remains x2, s1, s2, s3, but the s1 here comes out and this becomes x2, the s2 stays, the s3 stays, and this is now the new z. Alright, so let's think about this. X1 still doesn't have a value over here, so x1 is still at 0. X2 now has a variable value. It has moved to 11. X2 is at 11. S1 is now at 0. Its slack is 0. S2, the slack is 6. S3, the slack is now 35. Okay, and you can check that. You can see that that's going to be how this works, and it's in the feasible region. But note, Z has now become 66. So I have moved from one vertex 0, 0 to another vertex in the polygon 0, 11, and my objective function has increased from 0 to 66. Okay, so let's kind of move to a new page here. Okay, so let's tidy this up a bit. We just got a new matrix, right? Negative 1, 1, 1, 0, 0, 11, 2, 0, negative 1, 1, 0, 16, right? I think that is 16. Yep. 7, 0, negative 5, 0, 1, 35, and the objective function is kind of working out here to negative 10, 0, 6, 0, 0, 66. Okay, so we have this identified as x1, x2, s1, s2, s3. These are now x2, s2, s3, and this is still z down here. Okay, so this is my most negative entry in the bottom row, that negative 10 there. So we play this game. We say 11 divided by negative 1, that's no good because it's negative. 16 divided by 2 is 8, right? And then 35 divided by 7 is 5, so this is the smallest non-negative value. So we're going to pivot on that 7. Okay, so this gets a little wonky here, okay, because we're actually going to get some fractions here. All right, so we take the pivot row first, right? So this is going to become 1, 0, negative 5 sevenths, 0, 1 seventh, and let's see, 35 divided by 7 is 5. Okay, so I need these all to be zeros. Okay, so let's see. I gotta go 1 to 2 here, right? So 1 to 2. So this is going to be negative 2 to 2 is 0. That's still 0. Okay, so if I do this negative 2, that's like 10 sevenths minus 7 sevenths, so that's going to be 3 sevenths. This one is still 0. Or no, that's still 1 in that row, 1. And then, let's see, we're multiplying this by 2, so that's 2 sevenths there. Right, so negative 2 sevenths. And then, let's see, 5 times 2 is 10. From 16 is 6. Okay. So now we're just going to add these. So that's a 0, 1. Let's see, negative 5 sevenths. So that's going to be like 2 sevenths. 0, 1 seventh. And then 5 and 11 is 16. And now going down, we got to multiply by 10, right? So that's a 0. That's a 0. So that's 50. Let's see, 50 sevenths. Let's see, 6 is 42. So this should give me negative 8 sevenths. This stays as 0. And this comes down as 10 sevenths, right? And then what do we get here? We got 5 times negative 5 times that's 50. 50 and 66 is 116. Okay, so what did we do? X1, X2, S1, S2, S3. This is still X2. Right? This is now X1 and this is S3. This here is Z. So we pivoted again. All right, so x1 is now at 6, x2 is at 16, s3 is at 5, and z is at 116. Okay, so oddly enough, we are still not optimal here. That negative in the bottom row causes me a problem. Okay, so we're going to look just here for a moment. This is the most negative column in the bottom row. If you do a little bit of work with this, I'm going to ask you to trust me a little bit here. This is actually going to become the column we pivot on. Minor mistake here, right? We did not get rid of the S2. This is still S2. Haha. This is still S2. We got rid of the S3 with the one going out. So S3 is actually hanging here as X1. So X1 isn't 6. It is, in fact, 5, and this is 6. All right, so let's get that straight. Okay, I'm not going to walk through that entire last pivot. You can kind of try it for yourself. But if you do that last pivot, you're going to end up with 0, 1, 0, negative 2/3, 1/3, and coming down the column here, you're going to get 12. You have 0, 0, 1, 7/3, negative 2/3, 14, 1, 0, 0, 5/3, negative 2/3, and 15. And the bottom row comes out as 0, 0, 0, 8/3, 2/3, 132. Okay, so these columns are still x1, x2, s1, s2, s3. After the last pivot, this is x2. This is now s1. This is still x1. And my z value is here. So our location is x1, 15. x2 is 12. S1 is 14. Notably, S2 is going to be 0, S3 is 0. So we took the two slacks out of that constraint to make this. But my z value is now jumped up to 132. So this is yet another vertex on that polygon, right? It's 15, 12. And in fact, 15, 12 for x1, x2 is the optimal group. And so this is where it happens at. And this yields a z value of 132, which is as high as that z value can be given the constraints. How do I know this? There is nothing here in this bottom row that is negative. So if all of this slams into the positive direction, there is no way to go up from there. We have hit the top of the mountain. We are at absolute maximum. Z is 132. Okay, so good news is next time we have class together, I'm actually going to give you a piece of code. It's actually attached to this in the Google Classroom that allows you to do this. Okay, so that code kind of breaks this into 3 matrices. It's going to give you the coefficient matrix here, a B matrix here, and another matrix there. And if you enter those 3 matrices into the code, it will do the pivoting for you. Lots and lots of pivoting for you. It'll spit out the final tableau, and it will give you the optimal solution, because that's why we have algorithms. All right, so there you have it. This is Simplex, and we'll do some more examples with this later. Thank you.